Hi all, there is a short version, a sub 2-minute version of this quick chat about the 2019 Nobel Prize for Physics. But this is the longer, more detailed version for people who want the deep detail. So the 2019 prize was split two ways between James Peebles, received half of it, and a team of Michel Mayor and Didier Queloz received the other half. So I'm going to talk a little bit about the prize itself, and then I'm going to talk a little bit about each of those teams and the kind of work they did, what they contributed to our understanding of the universe. So the Nobel Prize was created by Alfred Nobel, who, among other things, invented dynamite. And I mean, and I think the kind of the mythical story, the Archimedes in the bath and apple falling on Newton's head story, is that he was kind of remorseful that dynamite had been used in warfare to kill people and felt that he needed to have a positive legacy as well as that legacy. And so created these prizes for peace, for medicine, for physics and chemistry, for a number of things, and endowed them with his fortune, which has continued to grow since. So the Nobel Prizes recognize peak achievement in these particular fields. This year, each Nobel Prize is worth 9 million Swedish krona, which is about 1.3 million Australian dollars. And quite often they will share that between the recipients. Now, you know, that's a chunk of money. Even if you get half of it, it's still a chunk of money. James Peebles mentioned in the press conference that most of it would go to charity, and then apparently got a glance from his wife and said some of it will go to charity and some of it will go to our children. So I thought that was kind of funny that was what happened with the money in his case. Of course, it's not just the money, it's the prestige. Basically, a Nobel Prize winner needn't buy themselves dinner again for life, pretty much. It's a recognition from your peers at the very highest level of your contribution to the work. So congratulations to these teams for their work. And it's fascinating work. It's why I wanted to create a bit of a video and chat a little bit about it, because it's just amazing. So we'll start with James Peebles. He was Canadian originally, so we can kind of claim him for us Aussie Canucks, or Canucks. He grew up was born in Winnipeg, Manitoba. But he basically moved to Princeton University in 1958 and has been there ever since. So he tends to be called Canadian American these days, although I was delighted to see in the press conference also that he said, I wanted to learn more about the universe. That made me very happy. So his quest since 1958 basically has been to understand the universe, and we've come to understand it enormously better since then. So there was some original work about the possibility of the Big Bang and the cosmic background microwave radiation that was done in the late 40s that he built on. But he was one of the people who predicted that the cosmic background radiation would be detected before it was actually detected. Penzias and Wilson actually detected it and got the 1978 Nobel Prize for detecting the cosmic background radiation. And despite the fact that some of people's work was before that, he's getting his Nobel now, however many years later, so 30 years later, 40 years later. So he has worked on that whole field of why is the universe as it is, how has it got here, and so on. And among the things that he's worked on and made a really big contribution to, there's a huge amount, and a lot of what he did was taking it from kind of speculative to very data-based. So cosmology now is a discipline of both optical and audio wavelength, radio wavelength, sorry, I'm trying to come up with the word, telescopes looking at the universe and dealing with data. So working with describing and understanding the universe in terms of the data, both the cosmic background radiation, the fact that the whole universe has a background temperature of about 4.2 Kelvin, 4.2 above absolute zero, which is leftover radiation from the Big Bang itself. The initial very rapid expansion has left this signature, which is not homogeneous around the entire universe. So you can actually read something about the history of the universe by looking at the background radiation. So Peebles has contributed a lot around dark energy and dark matter. Now, really briefly, and probably this is another video for another day, but the two things are not really related. The fact that they both have dark in the name is just kind of a historical accident of how they were named. They probably should be named something like occult matter, which then suggests Satanism or spiritualism of some kind, but occult just means hidden. But they're dark because we don't know what they look like. We can't see them, but we know they're there. How do we know they're there? Dark matter hangs around where matter hangs around. So in galaxies, not out so much out in free space, but it hangs around in galaxies between stars. And it seems to have mass, but be very difficult to detect and cause the rotation of galaxies and so on to behave as though there's more mass there than the visible mass we can see. So that's what dark matter does. We need to find out what it is. So there are various views and opinions about what it might be. Non-baryonic matter is one of the things that's talked about, but basically we don't know what dark matter is, but we know it's there by the way, or we know that we need to fix our theories so that we don't need this kind of hidden variable, because our galaxies don't behave in the way they would if only the visible matter were there. Dark energy is kind of everywhere through the universe, and it's what's causing the universe to expand faster than we would predict, again, looking at the mass only. We looked at the existing known matter, which we think is probably about 5% of all of mass energy in the universe. It would predict a particular rate of expansion for the universe. The universe is expanding faster than that, suggesting the existence of this dark energy. So again, we need to figure out what that is. And there's obviously much, much more work to be done on that, but James Peebles has played a huge contribution in that. So that's really, I guess, a quick rundown of his work. The other team, Michel Mayor and Didier Queloz, are both Swiss astronomers. They were working at the University of Geneva at the time of the discovery. And the really cool thing is that Didier Queloz was a PhD student at the time. And essentially what he was doing was just working on the apparatus to hone his skills in analysis and using the apparatus when he actually made this momentous discovery. So he and his supervisor have shared now the Nobel Prize some years later for this discovery of this first exoplanet, this first planet in another solar system. And it was only 1995. Now, to someone like my daughter Alexandra, who was born in 1994, that seems like a long, long time ago. To me, who was just starting my PhD in 1995, you know, it's a fair while ago, but it's not. It's very recent in terms of science. So, you know, we didn't know prior to that. So if you know, half my life, something like that, we didn't know whether there were planets outside this solar system. It seemed reasonable to assume there would be, because there were so many planets in this solar system. It seemed reasonable to assume there are so many other stars, there must be planets. We didn't know, we didn't have evidence until 1995. There may have been other objects detected, but this was the first one around a sort of Earth-like sun, a sun at a similar stage of life and a similar size to our sun, and a planet was detected. Now, there are a couple of ways that we detect planets around other suns. One is, if you imagine the sun and you imagine a planet going across the front of it, you're decreasing the brightness of that sun by a tiny, tiny amount. Now, the size of a planet relative to the size of the sun is very tiny. So you need very, very, very fine detection to detect that. But if you get this pattern of the light of the sun dims by this much each, on a regular pattern, then you can figure out that it's probably a planet going across, and then you can figure out the length of its orbit and various other things from that. So that's one way that we detect extrasolar planets. The other way, which is the way that these guys used, is a little more complicated and sophisticated, but it works really well, which is that planets and planets don't really just orbit the sun, in the sense that the sun stays absolutely stationary at the center and the planet goes around it. What actually happens, because they both have mass, they both actually orbit the barycenter, which is the center of mass of the two of them combined. Now, our solar system is complicated because we have 8 planets of various sizes. So the sun is actually wobbling in relation to a bunch of things at the same time, all of which have different year lengths and different orbits. But so you really probably want a quite simple system with 1 or 2 planets to make it possible. But that means that the sun wobbles a little bit on its orbit. So the metaphor that I often use is if an adult and a small child are holding hands and spinning, The adult will move a little bit because they're still moving around the common center of mass, but most of the mass is in the adult, so they won't move very much. If two adults hold hands and spin, they will spin probably around about the point where their hands are if they weigh the same as each other. The barycenter, the common center of mass, will be right in the middle between them. And depending on the relative masses of the suns and the planets is where that barycenter is and how much the sun actually moves. So in this case of this particular one that they found in Pegasi, they found that you could actually detect the sun moving slightly toward us because you got a very slight blue shift in the light coming from the sun. So a blue shift shows that a source of light is moving toward you, and a very slight red shift as it moved away, and then a very slight blue and red and blue. Only very, very slight, but you had to be able to detect that in the light from the star. The light from the star also tells you things about the mass of the star and its composition and its age and a whole variety of other things. But these regular variations in the color tell you the orbit of the planet around the star. And it turned out to be very weird. You know roughly the mass of the star, so you can work out roughly the mass of the planet. The mass of the planet was around the size of Jupiter, so a big, big planet, the biggest planet in our solar system by some significant distance. But the year of Jupiter in our solar system is 12 Earth years. It takes Jupiter, it's bigger and it's further out. It takes 12 times as long for it to go around the sun as it takes us on Earth to go around the sun. So 12 years. But this planet that Mayor and Kellos discovered had a year of 4.2 days. So it was very close to the planet, which obviously helped with being able to detect it because it was a big, massive planet and it was very close. So it had a short year. So you got these quick variations in the light rather than over a 12-year cycle, which is obviously a lot harder to pick on a human timescale. So as I say, they discovered the first, and it was a very exciting discovery, and we've gone on to discover thousands now using a variety of different methods of various sizes. Originally, they could only discover the really big ones, the Jupiter scale ones, but now we're getting close to being able to discover Earth-size planets or close to Earth-size planets. And you'll hear announcements every now and then about a nice Earth-size planet in the Goldilocks zone where it's not too hot and not too cold to have life. None of them are going to be as good as Earth, and I could get it into a whole other rant about we need to protect this Earth because no planet is as good for us as this Earth is, kind of by definition because we fit this Earth. But that's possibly, again, another talk for another day. So I hope that gave you a useful sense of the Nobel Prizes, who they're awarded to, what kind of work they're awarded for. And frankly, that this is very exciting work. It gives us a sense of who we are and our place in the universe. And often people will end these kind of things by saying we're insignificant in the vast universe. I don't believe so. If you go the other way down to the quantum scale, we're vast ourselves. We're the same size we always were, but now we know more, and knowing more is good. Thanks very much. Have a good one.